Alrighty, so I guess today we will practice some line integrals. So I'm going to focus mostly on 16.2 today, where we evaluate everything directly, so to speak, using the direct formulas from section 16.2. In 16.3, we talked about a special shortcut that applies for special vector fields. In particular when they have anti-gradients or potential functions, whatever you want to call it. But for today, let's just do it the way that'll work for pretty much any vector field. Okay, and I should say for any vector field, at least the setup. You might get impossible antiderivatives that you have to do, but we're not going to really worry about that. But this is the setup that in principle will work to do a line integral over any type of vector field, any type of scalar function. Alrighty, so first thing I want to reiterate is a confusing point I've noticed over the years teaching this, is that there are two distinct types of line integrals that you want to make sure you keep straight in your head. There's the first kind where you're integrating a scalar function with respect to arc length. So remember back for 230 folks, back in chapter 13, we used S to denote arc length. For those of you 232, hopefully you remember from whenever you took 231 that that was the case as well. So S is our standard variable for arc length, so this d little s stands for with respect to arc length. Okay. As far as what this represents, if you do the boring constant integrand f equals 1, so you're just integrating the line integral of 1 ds, which of course you could just rewrite as line integral of ds, then that just gives you the arc length. And so that's consistent with what you had from Calc 1, where you do the integral from a to b of dx, you just get b minus a, which of course is the length of the interval of integration. Back in chapter 15, when we did the double integral of the boring constant function 1, we got the area of the region. And also in chapter 15, when we did the triple integral of the boring constant function 1, we got the volume of the region of integration. So in general, we have this idea that when you integrate the boring constant function 1, you get the size of the region of integration. And so it's going to be the appropriate notion of size. So for one-dimensional things, size means length. For two-dimensional things, size means area. And for three-dimensional things, size means volume. Okay, so anyway, that's the boring constant integrand case. And then otherwise, you want to think of your integrand f as being some kind of linear density function. So for example, maybe it's the grams per meter of some kind of wire. So let's say you have some wire, I'm just considering this, and maybe it's made out of different metals. So parts of it are made out of gold, parts of it are made out of aluminum, and gold, of course, I'm pretty sure is a lot heavier than aluminum. And so, you know, if this part of the wire is 90% gold, then it has a certain density. And that's, let's say that it blends and gets, you know, more aluminum based in this part of the wire. And so you have a different density value here. And so this integrand f could tell you the local, it tells you the density at each point on the curve. In which case, when you do the line integral of the density function, with respect to arc length, you get the total mass of the wire. So that's the idea. I don't know if this idea of different blends of metals of various densities is a little bit too confusing for you. Maybe just think of F as the density of cars on a road of some sort. So you have in areas of high congestion, maybe there's, I don't even know what appropriate units are. I don't know, whatever, but like you have a certain number of cars per length, you know, in a traffic jam that's very high when you have bumper to bumper traffic. But then on the highway, if you're in the middle of nowhere and the cars are more spread out, the number of cars per mile is a lot lower. And so anyway, if you have this integrand f, which tells you the density of cars at particular places on the road, when you do the line integral of this car density, you get the total number of cars on the road. So I think that's a good practical interpretation to help you keep things in mind. Okay, so the formula, the way you figure out the first kind of line integral is you have to get your hands on a parametrization or a vector function, however you want to call it, that traces out your curve C. And so once you have that, basically you do f of r of t times the length of r prime of t dt. So for this first kind of line integral, ds is a scalar. There's no bold anything, but we have the length of r prime of t dt. So that's what you want to think of for this. Okay, and so let's contrast that then with the second kind of line integral, which is when you have a vector field integrand. And so not only is there a vector field here in this integrand, but also this d vector r is a vector quantity. And then in addition, you really have this dot product. So if you're being careful with your notation, you're labeling things as vectors, you're not using dots to represent good old regular multiplication. If you're being careful with your notation, then it should be really clear what are vectors, what aren't vectors, what's going on as far as dot products go. And so for this second kind of line integral, there is in fact a dot product happening here. Okay, and so basically this is, you want to think of this vector field integrand f as being the force field. And so remember, forces or vector fields you could think of as just being a bunch of arrows pointing in various directions. For one simple model of gravity, right? Force is just pointing straight down. But I guess if we think of the Earth as actually being round, I guess then the force points directly towards the center of the Earth. And so anyway, you could have all kinds of different forces. And this second kind of line integral tells you the work done by a particle, the work done by the force field on a particle taking the path c. So I think in physics, you usually talk about the work done by the particle, but our convention, there's a minus sign that we're off a little bit here. We're talking about the work done by the force field, and they're just related by a minus sign. Not very important at all. And so then the somewhat little tricky thing about this second kind of line integral is that sometimes it's written in slightly different notation. So I remember really being weirded out the first time I saw something like p dx plus q dy, because the only other type of thing we've ever seen dx's and dy's together in, remember, is double integrals where it's multiplied together, so to speak. But this p dx plus q dy, that's something we really haven't seen before this week. And the way I like to think about it, so the book somewhat suggests like it's a third type of line integral, but I think it's much easier and it's correct to just think about it as alternate notation for the second type of line integral. So if you remember when we started talking about vector fields on Monday, we usually name the component functions of our vector field P and Q for the 2D vector field case. So our vector field F is equal to P comma Q. You want to think of this D vector R as being dx comma dy, which kind of makes sense because throughout this course we've thought of, and also in physics, this R vector stands for position vector. So the position vector is the vector with components of the x and y coordinate of a particular point. But anyway, think of dr vector as being dx comma dy, so that when you actually do that dot product, you get p dx plus q dy. Okay, and so that just different ways of writing the same thing. So once you want to go and calculate this second type of line integral, it's the same story. Basically, it's all about getting your r of t for your curve C. But once you get it here, you're going to do something a little bit different with it. You're going to do f of r of t dot product of the vector r prime of t dt. So whereas ds, remember, was the length of the vector r prime times dt, the vector dr vector is the vector r prime of t dt. So keep that straight, and you're actually doing the dot product here. Okay. So I figured today, just do a few examples, really emphasize doing these directly. But before we get into that, let's just review what we had on Monday as far as some useful parameterizations to remember. So as you can see here, it's all about getting the r of t for your curve C. So basically what I want to do now is just refresh your memory on some different r of t's that you should be prepared to set up. So the first one would be a line segment. So if you want to go from a point with position vector r0 to a point with position vector r1, you're going to do, well, if you think back to chapter 12, the ingredients for a line, you need a point and a direction. So the direction is going to be the displacement vector between these 2 points, which is just going to be the difference in these displacement vectors from the relative to the origin. And then your point, of course, you could do r0. So there are other combinations. You could do r1 plus t times r1 minus r0. But the whole idea is that if you memorize and use this exactly, then it's guaranteed to be 0 to 1. So if you start messing around with this, you might have to figure out which t values give you the given points. But it's pretty clear here that if you substitute in t equals 0, well, if t equals 0, you get r0. So we're starting at r0, so that's good. And then if t equals 1, then the r0s cancel and you're at r1. So like I said, there's always infinitely many different ways you can parameterize any given curve. And you'll get the same answer if you do that, a different parameterization. It turns out that you'll get something that's linked through a U substitution. Maybe I'll show you that in a second. Maybe I'll show it to you on one of these examples. But anyway, as long as you're doing a correct parameterization, it should work. But I think it's just good to get used to this exact one, because then you don't have to fuss around with trying to figure out what t values you have to integrate between. So if you do that exact setup, you'll always be 0 to 1. Okay, and then not all curves that we're going to be dealing with are line segments. So you might have to do something, trace out the curve y equals f of x. And so again, there's infinitely many different ways you could do this. If you wanted to get complicated, you could do t cubed, f of t cubed. You could do, t to the 5th, comma f of t to the 5th. All that's important is that your components x and y satisfy that y is f of x. So there are infinitely many correct choices for how to parameterize y equals f of x, but my motto is the laziest correct way to do something is always the best. That's how I try to live my life. And the easiest way to do y equals f of x is to just let x be t and y be f of t. And then clearly y does equal f of x. And then you could do the same kind of thing if you turn this on its head and have x in terms of y. The reason you might need to do this, remember, if y is a function of x, there has to be some vertical line test that's passed. For x to be a function of y, you have to pass the horizontal line test, because remember, this whole notion of function has this thing built in that there's only one output for each input. But anyway, it's good to be flexible, and depending on how you're given these equations, you might not want to spend time trying to solve for y or solve for x or whatever. So if you're given x in terms of y, might as well, just let y be t, and then x is going to be g of t. The only thing that's a little bit different is, when x is t, you're looking at the x values to figure out the t values. But when y is t, you're looking at the y values to get the t values, which if you just pause for a moment to make sense, to think about it, it should make sense. And then finally, if you want to parameterize a circle, you could solve for x or y, but you can't trace the entire circle with one thing because, right, like if I solve for y here, this would be y equals plus minus square root of r squared minus x squared. And so if you wanted to trace out the whole thing, you'd have to do the top half with the plus, you'd have to do the bottom half with the minus. And also square roots are kind of nasty when you start taking derivatives, which we're going to have to do because remember, both of these formulas involved r prime. So if we can avoid putting square roots in r, we probably should. And so anyway, the best way to trace out a circle is using cosines and sines. So in that case, t is basically functioning as your polar angle. So your t limits are going to come from the angle that you're talking about in this circle. All right, so yeah, let's just do a few examples. So calculate the line integral x ds, where c is the part of x equals y cubed between 0, 0, and 8, 2. So I think it's a really good habit to get into, especially as we're going to be continuing on into more complicated shortcuts that are potentially available, is to just always figure out what type of problem this is asking. So this is the first kind of line integral. This is our scalar function with respect to arc length. And this is, I guess you want to think of this scalar integrand x as representing density of cars on a road or density of mass in a wire, something like that. And so this is like the mass of a wire, if the x is the density function. And so our shortcut, or the way we calculate it, it's not really a shortcut, we absolutely have to do it, is we get our r of t parametrization for our curve C. We do f of r of t times the length of r prime of t dt. Okay. All right, so let's think about how to do our r of t. So one mistake I've noticed over the years is a lot of times people assume everything is a line segment, and that is not the case at all. It says we're supposed to integrate x equals y cubed from 0, 0 to 8, 2. So basically that's the cube root graph, y equals the cube root of x. And so this is our curve C that we're dealing with. So our wire is bent into that shape in the xy plane. It looks like the density is x, so it's lighter here when the x value is smaller, and then it's heavier over there when the x value is bigger. And so our goal is to then figure out what's the total mass of this wire, where it seems like it's heavier towards the right-hand side of it, according to that density function. Okay, so it's all about getting our hands on r of t. And so notice this falls into this framework right here. We're given x in terms of y, so we might as well let r of t, so the best way, I'll call it, is to let y be t, so that we're basically looking at t cubed comma t. Because remember, if y is t and x is y cubed, x is t cubed. And I think it's a good check every time you're setting up a parametrization. So I'm letting y be t, so it's the y values of these points that I'm looking for to get the t bounds. But again, if you're ever not sure, just plug it in. So if I do r of 0, r of 2, r of 0, according to this formula, is 0, 0, so that's good. R of 2 is 8, comma 2, so that's good. So like if you accidentally got a little bit goofed up and did, 0 to 8, you'd get 8 cubed, comma 8, and so that would be no good. So there's really no excuse for getting these bounds wrong, because you can always take a couple of seconds here and plug in to confirm that you get the given endpoints that were wanted, that were asked for. Okay, so anyway, that works for r of t. So we got to get our hands on r prime of t, which is 3t squared, comma 1. We got to get our hands on length of r prime of t, which is square root of 9t to the 4th plus 1. That's all we can do. We can't do anything else. And so then x ds becomes, again, it's the components of r that are x and y, so t cubed times the square root of 9t to the 4th plus 1 dt. So this is ds. Remember, ds is length of r prime t dt, and then x, of course, is t cubed. And so from there, if you hit that with a substitution, u equals 9t to the 4th plus 1, 1/36 du is t cubed dt. I've already started rearranging it based on what I actually see. You get 1/36 2/3 u to the 3/2 between 0 and 2. I guess I forgot to do that. 0 and 2 were our t-bounds, so those go here. And so whatever this ends up being, what is that, 145 to the 3/2 minus 1 to the 3/2, which is 1. Yeah, 9 times 16, it's 144. And then 3 times 18 is 54. But whatever, nothing too terribly complicated there. So anyway, you might be wondering, I mentioned a few minutes ago what happens. So that's the best way. So I said that any correct parameterization you use should give you the correct answer. So let's see if we can figure that out here. So something else you might be tempted to do here, so another way would be, and I don't like this as much because you're doing more work. You could take this x equals y cubed and change it to y equals x to the 1/3, in which case your r of t, if you let x be t, you could be t comma t to the 1/3. And then in that case, that would be 0 to 8 would give you the thing. So again, there's infinitely many different parameterizations. There's no single set of correct bounds. The whole idea with the bounds is that they have to be correct given the parameterization that you're using. So that's why I think it's a good idea, like I said over here, to check that whatever parameterization you're using, that it works out. And so if you do that over here, notice, yeah, that r of 0 is 0, 0, and then r of 8 is 8 comma cube root of 8, which is 2. So there we go. So like I said, there's no single correct answer, but your bounds and your parameterization have to be compatible to give you the piece of the curve that we're talking about. Okay, so anyway, let's continue setting this up. R prime of t is 1 comma 1/3 t to the minus 2/3 is the derivative. And then length of r prime is square root of 1 plus t to the 4/3 over 9. And so if we set it up using this parameterization, we get the integral from 0 to 8 of t. Well, I'm going to use a different variable here. The name of the integration variable isn't important. So let's just do everything in terms of u. So let's name the parameter u, because again, the name of this integration variable is not important at all. So if I set things up in terms of this, I'm going to get the integral of x. So x in this case is u. And then ds in this case is 1 plus u to the 4/3 over 9 du. And so now I claim, so I guess first of all, you could set up something that's ridiculously scary looking. I mean, it turns out it will be possible to solve it. If it's possible to solve it in terms of one parameterization, it's going to be possible in another. But it might be scarier looking, and it might be more difficult to figure out what the hell's going on. So when we write these problems, we're going to assume that you take the laziest way. Because if we don't, then all bets are off. You guys can make some very complicated intermediate steps. But for x equals y cubed, we're going to make sure that it's not so bad of an integral to do if you let y be t and let x be t cubed. So if you put yourself through doing extra work and solving for y in terms of x, like I'm doing over here, you might get something that looks a little bit more complicated. And yeah, I'm not just looking at this, I don't know how I would proceed immediately. It turns out if you mess around with it enough, it will be possible to do. But anyway, so I made the claim that as long as if we forget about the whole idea of actually being able to do it without too much work, these integrals should be equal, right? Because we did correct parameterizations for each. So I claim that these are equal. And so, okay, the thing that links these is a substitution. So let u equal t cubed. Okay, so I guess if I want to convert this one into that one, I would be letting u equal t cubed, and then du is 3t squared dt. So if I start subbing in, this would give me, and then I guess when u is 0, t is 0, and when u is 8, if 8 is t cubed, then t is 2. So my bounds change to 0 to 2, and then u becomes t cubed, and then I get square root of 1 plus, so u to the 4/3 is t to the 4th over 9 times 3t squared dt. And does this end up working out? Did I mess something up? Sorry, let me pause this real quick. I'm just having trouble seeing this. Aha, I see what I screwed up. This was u to the minus 2/3 was in our r prime. So when I square that, I could do it like this. This is going to be 1 over 9 u to the 4/3, because yeah, the negative exponent on u gives me that, which means that this is 1 over 9 u to the 4/3, which now I make the substitution. That's exactly what went wrong. 9t to the 4th. And so then when you distribute this 3t squared into the square root, that gives you precisely 9t to the 4th plus 1 underneath. So anyway, that's what happens. If you choose a different parameterization, you might get a different looking integral here. However, it's always going to be equal to the integral you get from another parameterization. They're going to be linked through a substitution that basically links the parameters that you chose for either case. So anyway, don't worry too much about that. The purpose of that last few minutes was to tell you that as long as you're using a correct parameterization, you will get the same answer. But anyway, in general, when you come across something, find the simplest parameterization that works. So if you ask me, t cubed comma t is simpler than t comma t to the 1/3, because these fractional powers, you end up getting messier derivatives and scarier looking integrals here. But end of the day, rest assured, as long as you're using a correct parameterization, you will get the correct answer. Okay. So anyway, that's that one. Let's just take a look at a couple more. So calculate x cubed dx plus y squared plus x dy, where c is the part of a circle in the first quadrant and then a line segment. So the first thing, like I said in the previous example, I always like to figure out which type of calculation this is. So again, this is the alternate notation for the vector field work. So remember, you think of dr as being dx comma dy, and then you think to yourself, okay, for which vector field is that the dot product with dx comma dy? Well, the vector field x cubed comma y squared plus x. So we're calculating the work done by the force x cubed y squared plus x on a particle taking path C. Okay, so this one we're going to have to break it into two pieces. So let's start thinking about this picture. So it says we're in the xy plane, and it says that we first take the first quadrant part of this circle of radius 2 from 0, 0, from 2, 0 to 0, 2. And then we take a line segment from 0, 2 to 4, 3. So basically, we're just going to have to split this calculation into two pieces and figure out the work on the first piece, figure out the work on the second piece, and then add them together. So let's call these piece 1 and piece 2, or whatever. We could call it, let's call it C1 and C2. So that curve is C1. This curve is C2. So work on C1. Okay, so for C1, you could do r of t is t comma square root 4 minus t squared from t equals 2 to 0 would take care of it. T equals 2 to 0, because with these work questions, you do have to pay attention to which direction you're going. So if you read carefully, it says we're from 2, 0 to 0, 2. So you have to make sure that when you trace out your curve, you're going in the proper direction. So you could do that, but again, that caused me to do extra work here. I had to play around and solve for y in terms of x, and then let x be t, and I don't want to do that work, first of all. Second of all, that square root is not going to be fun in r prime. So I think it's better to remember that cosines and sines are the best way to trace out a circle. So instead, I'm going to use 2 cosine t comma 2 sine t as the r of t for this first curve C1. And then if I'm doing cosines and sines, then essentially t is the polar angle. The t is going to be your counterclockwise angle from the positive x-axis. And so to trace out this quarter circle, we're going to want to start at t equals 0 and stop at t equals pi over 2. And you could plug in t equals 0, you get 2 comma 0. T equals pi over 2, you get 0 comma 2. So we're looking good. Okay, so then we're doing r prime is minus 2 sine 2 cosine. And so again, you're going to want to practice these. For this work type of line integral, we don't take the length of r prime of t. Remember the first kind with d little s, we did take the length of r prime of t, but for this one, we do not. So just pay attention to all these little details. So then I have to do f of r of t. So f of r of t, I'm basically plugging in x is 2 cosine t, y is 2 sine t into my vector field, which is x cubed. So 2 cosine t cubed, y squared plus x. So that's my f of r of t. Now I do f of r of t dot product r prime of t. Okay. And so that's going to be, I'll multiply some things out. That's going to be what? Negative 16 cosine cubed t sine t plus 8 sine squared t cosine t plus 4 cosine squared t. So dot product is a scalar. Don't leave it as a vector. That's a big no-no. Yeah, that looks good. So the work on the particle taking the path C1 is going to be the integral from 0 to pi over 2 of this f dot r prime, so minus 16 cosine cubed t sine t plus 8 sine squared t cosine t plus 4 cosine squared t. And then, okay, if you do a substitution, u is cosine t on the first term, if you do u equals sine t on the second term, and then the third term, you're going to have to use the fact that cosine squared is 1/2 plus 1/2 cosine of 2t. We've reviewed this double angle formula before when we were doing polar coordinates, and spherical came up a few times. But anyway, it looks like our antiderivative is 4 cosine to the 4th t plus 8/3 sine cubed t, and then plus, well, this is going to be 2t plus sine of 2t after I do my anti-differentiation. After my double angle identity. And so, okay, we're going to get 8/3 plus pi. And then at 0, we'll get minus 4 because cosine of 0 is 0. Cosine of pi over 2 is, sorry, cosine of 0 is 1. Cosine of pi over 2 is 0. So whatever, I'm just plugging in and subtracting. No big deal. Yeah, looks good. So that's our work on C1. Now we're going to have to do the work on C2. So C2, I have to come up with R of t. And so I'm going to use the line segment situation. So our starting point is 0, 2 plus t times our ending point minus our starting point. So R of t is what? 4t, 2 plus t. And again, if you do it in that exact framework, start plus t times end minus start, it'll always be 0 to 1 for your t bounds. And then from this stage, you do the same kind of thing. R prime of t is 4, 1. F of R of t. So this is our x, this is our y. For this piece, what was x? P was x cubed. So 4t cubed, comma, y squared plus x, and then I do this dot product, f dot r prime is, well, what's 4 to the 4th? Is that 256 t cubed plus 2 plus t squared plus 4t is what I get for the dot product. So I do 0 to 1, 256 t cubed plus 2 plus t squared plus 4t. My antiderivative is 64t to the 4th plus, I could multiply this out, but I might as well do a substitution instead. 2 plus t cubed over 3 is the antiderivative, and then 0 to 1. So 64 plus 27 thirds is 9 plus 2, but then be careful. At 0, you get a contribution from this. So at 0, you're going to get minus 8 thirds. So the total work is whatever we got for C1, which was 8 thirds plus pi minus 4, plus whatever this is. What is that? 75 minus 8 thirds. So that's 71 plus pi. Nothing too exciting at the end. Big thing, though, is realizing that we have this circle piece and a line segment, and you use a circle cosine and sine parametrization for the first piece. You do a line segment parametrization for the second piece. You do f of r of t dot product r prime on each, and there we go. So I'm just thinking real quick, so checking my work, make sure I like this. Yeah, sorry, I was cheating with some extra techniques and just making sure that sounded right, and it is right. All right, so last example for today is this, just a 3D example. So calculate work done by this vector field F. So work of F on a particle taking the path given by that straight line segment. So just to reiterate, nothing really changes in R3. I guess when you go to R3, your other options here are a little bit trickier to deal with. So if we give you like a R3 situation that we expect you to solve like this, then it's either going to be a line segment, or we might give you the R of t, or it's just not going to be so bad to figure out. But anyway, this is pretty much the same thing we just did. R of t, if we do start plus t times and minus start, we get 0 to 1 plus t times 2, 3, 0 minus 0 to 1. So we get R of t is what? 2t, 2 plus t minus t. And so again, I think it's good to just, plug in t equals 0, t equals 1. Oh yeah, and as you can see, I screwed something up here. This should be 1 minus t. Take a couple seconds and plug in t equals 0, t equals 1 to confirm that you get what you want. So 0, 2, 1 looks good at t equals 0, and then 2, 3, 0 looks good at t equals 1. So again, just take a few seconds, plug those in, make sure you get the start and the end that we want. Okay, so then r prime is 2, 1, minus 1. And then f of r of t, well, r, remember, is the components of x, y, and z are the components of r. So f is xy, so xy, comma, 2yz, 2yz, comma, 4zx, 4zx. And so basically you do 0 to 1 of f of r of t dot product r prime of t. So if I do that dot product, I get What is this going to be? 8t plus 4t squared plus, well, this is going to be 4. So it's going to be plus t minus 2t, so minus 2t minus 2t squared, looks like. So yeah, that's 2 plus t minus 2t, so minus t squared, so minus 2t squared. And then minus, this is what? 8t. Yeah, because that's plus 4t. Or no, sorry, that's plus 8t. And then minus 8t squared, so plus 8t squared. And then there, it's not so hard. It's just a polynomial. So finish that off. But yeah, so be ready to do line segments. But again, not everything's a line segment. That's an issue I've seen teaching this before. People are too eager to set up line segments. So anyway, that's that. Alrighty, so then the last little example is just consider this vector field given below. Draw curves C1 and C2 such that the C1 work is positive and the C2 work is negative. So again, you can remember that this formula is f of r of t dot product r prime of t. So you're doing the dot product of f and r prime. And so, okay, maybe for 232 folks who haven't thought about this in a while, when you have two vectors, a and b, their dot product is positive when they make an acute angle between them. It's negative when they make an obtuse angle with each other. And the dot product is 0 precisely when the vectors are perpendicular or a right angle. Because the dot product is equal to the product of the lengths times cosine of the angle between the vectors. So yeah, theta is the angle between vectors a and b. So think about when cosine theta is positive, when it's negative, when it's 0. And so intuitively, it just kind of makes sense. Like, think about if you're rowing with or against the current. So for example, this seems to have some it looks like a clockwise swirling. So if I let C1 go like that, the tangent vectors to C1 and the vector field are making an acute angle with each other at all points. Whereas for C2, you could do something where you try to have it go with the current for part of it and against the current for part of it, but you could also just kind of try to make it so that it goes perpendicular the whole time. So maybe C2, you have be perpendicular to the vector field at each point. So anyway, that's just, again, a refresher of what this f dot dr represents. You're sort of looking at how well does the vector field line up with the tangent vectors to your curve. So anyway, that's the story for 16.2. It's pretty much all I had planned for today. So I will see you later. Have a good couple of days.